Okay, so this is the beginning of the energy unit, but before we can kind of get into the idea of energy, we need to talk about a force that we haven't talked about yet. And the reason why we didn't talk about it in the forces chapter was because spring force, it behaves a little bit differently. And so let me kind of give you the basics of spring force and kind of give you then an understanding of how it's different from the other forces we've looked at. So the spring force is essentially a force needed to push or pull an elastic object. Elastic / stretchy object. And we symbolize, it's like a rubber band or a spring, we symbolize it as F sub S for spring. The equation for it is Fs is equal to negative Kx, where x is the distance stretched or compressed, and I guess I'll write over here, K is what's called the spring constant. And essentially, it is a measure of the stretchiness of an object. So the measure of an object's stretchiness. And if we think about the units for spring constant, the units for spring constant are newtons per meter. So it takes a certain amount of newtons to stretch it a meter, okay? So if it doesn't take a lot of newtons to stretch it a meter, it's got a really low K value. So an example of something with a really low K value is like a slinky. It's super easy to stretch it a meter, okay? So it has a really low K value. It may have a K value of like 10 newtons per meter. An example of something that has a really, really high K value, something that's really stiff, would be like the suspension on your car. It's really, really hard to stretch that. Another example of kind of a high K value is, I've got my ring stand here. So this is something that has a pretty decent K value. It's not like a slinky, but if I were to put my 1 kilogram mass on it, you can see, I don't know if you can see that. I'll hold it up. Oh, golly. Okay. So it's stretching it. Now, the thing that is kind of unique, move this out of the way, about this force is this force depends on the distance, okay? And it depends on the distance it's stretched and the direction. So spring force, something to note, is the negative in the equation indicates that the direction of the spring force is opposite the direction it is stretched or compressed. Okay? So the negative in the equation indicates spring force direction is opposite the distance stretched, compressed. Meaning, if you were to stretch the spring down, like the displacement, the x value is down, but the spring force is up. The spring force wants to kind of pull it back up. Spring force is a restoring force. So it wants to put it in the opposite direction. It wants to make it go back to the way it was. The other thing that is unique about spring force is because it's dependent on x, it is continually changing. So in my little model here, bring it back. Okay. There's a certain amount of spring force that is pulling this up, and right now it's being balanced by the force of gravity. Okay, so there's a spring force up and there's a weight down, and it's in equilibrium. But if I were to stretch the spring even more, the x value got bigger. And if the x value got bigger, the force got bigger. And if the force got bigger, if the spring force got bigger, it means that the weight is no longer able to compensate for the spring force, okay? So remember, right here, you can imagine, let me erase this. Right here you can say, you can imagine, okay, here it is. That's my awesome spring. It's staying still. So right now the spring force is equal to the weight. So right now these two arrows are equal to each other. It's in equilibrium. The net force is 0. But if I were to stretch it further, so now I've stretched it even more. Well, spring force depends on x. So this means if I stretched it even further, like if I went down an additional x value, okay, so we can see here, I've moved it down. So that means my spring force is going to be even bigger. And I'm going to represent that with a larger arrow. So my spring force is bigger. My weight hasn't changed. Like this thing is still 1 kilogram. So my weight arrow has to stay the same. So if I pull it down further, now I have a larger upward force than I do a downward force. It's going to move up. Now watch what happens, right? So if I pull it down, right now my spring force is bigger than my weight, so it's going to pull it up. It's going to accelerate, so it accelerates up. Okay, right up here. Now when I get to this point, this is going to be tricky to draw. I can do this. When I get to this point, it's as if now my object's up here. And if my object is up here, like it's moved up, my delta x or my x value's gotten smaller. So now, oh gosh, now my spring force is small, but my weight hasn't changed. My weight is still the same. Is that the same? Maybe here. My weight is this, golly. My weight is the same size. So when it gets to this point, now my spring force is small and my weight is bigger than my spring force. So my weight is going to cause it to accelerate down. And, oh gosh, that was too far. Okay. So you can see, like, as it's moving, the fact that it's moving up and down is because I have unbalanced forces. My spring force keeps changing in size. It gets small, big, small, big. And because my spring force is changing in size and my weight is staying constant, I end up having this varying acceleration. So spring force is tricky because the fact that it has a varying acceleration. We cannot use kinematic equations because kinematic equations are only for constant acceleration. And it's tricky to analyze forces with a spring force because of the fact that that A value is changing, right? Like if we think about this, vertically I have spring force minus weight equals MA. The problem is that this is changing, so this is changing. So I can really only kind of look at this as like a snapshot in time. So because of this, we tend to look at springs through the lens of energy because it's a little bit easier to analyze because energy doesn't have a direction. So that's why we don't talk about spring force in the forces unit, okay? But we'll look at the energy in a little bit, but right now let's just kind of understand how the mathematics of this work. So we're going to do an example of spring force. So this says that, here, it says a 0.15 kilogram mass is suspended from a spring and descends a distance of 4.6 centimeters. An additional 0.5 kilogram mass is added. What is the spring constant and what is the final displacement of the spring? So let's just kind of like visualize this. I have this spring and then I add this 0.15 kilogram mass, and when I do that, it moves downwards 4.6 centimeters. I'll have to convert that. And then I add, I've got this 0.15. And I add another mass of 0.5. And it's going to move down even further. if I were to kind of think of this as being my x equals 0, it moves down even further, okay? So the first part of the problem just says, what is the spring constant? So what is K? So if I think about this kind of through the lens of forces, right here, draw a force diagram, I've got spring force, and I have the weight. Now, I have drawn the spring force to be upward. Spring force can be lots of different directions. It's not like weight, where weight always points down. It's not like friction, where it's always opposite of velocity. Spring force is always opposite displacement. Like, that is why the equation is negative kx. So the fact that we have drawn the spring force upwards, like it's opposite this distance, this is my initial x value, I have taken into account that negative sign right here by drawing my force upwards. So when I go to actually do my equations and say spring force minus weight equals ma, and it is in equilibrium, so this becomes 0, and so my spring force just equals my weight. When I go to plug my value, like my mathematical model in, I'm just going to put kx. Okay, so again, let me reiterate. I do not put a negative here. The reason I don't put a negative here is because I have taken that negative into account when I drew my spring force in the opposite direction of the displacement. Okay? So now I just need to plug and chug, right? So K, my x value is 4.6 centimeters, so I got to be careful. That's 0.046 meters is equal to my mass of 0.15 times gravity of 9.8. And so you're all good students. You're going to pause the video. You're going to get out your handy dandy calculator. You're going to actually crunch this. This is just good practice of crunching numbers in your calculator. You should get a value of 31.96 newtons per meter. Okay? So that's the K value. The second part of the problem says, what is the final displacement of the spring? So now that we've added a 0.5 kilogram mass, what is like the new x value? So I'm going to move my board down because I've run out of space to work. Nothing has changed with my forces. Like, I still have a spring force going up. I have a weight going down. So in terms of my mathematical model, I still have this relationship. This relationship is still true. I'm still going to have, left over some of forces, I'm still going to have the fact that kx is equal to mg. But now I know my K value, because spring constant, it's a constant. It's a constant for a spring, unless like you mess up the spring. So if you ever had a case like a slinky and some not so smart person just overstretches it and then it never kind of goes back, then you have changed the K value. Okay, but we're assuming our spring constant is going to stay the same. So I still have this K of 31.96. I'm looking for this new x value. I'm looking for what's now my total distance stretched. My mass is this total, so 0.15 plus 0.5 times good old gravity. And again, you're good people. You're going to stop the video. You're going to solve for x. And I get that it is 0.199 meters. So my final distance that it stretches down is roughly 0.2 meters. Okay? So that is just an example of spring force, and we won't look at spring force too often. We'll look at more spring energy, but that's the basics of it.